Good evening everyone, I am Mr. Ish. Thank you for joining me for this video. We'll try to make this video an interesting one because we're going to be talking about a less formalized of a topic. We'll break away a little bit from a very concrete subject and look at something of this nature, free fall, an interesting phenomenon. I've presented a video on the calculus of free fall, and you know from that video we showed how this formula can be derived. An object's position with regards to it being in a free fall is given by this equation, half gt squared, where g is a gravitational constant indicating acceleration. Since objects in free fall are going downwards in terms of their vectors and directions, you can put a minus over here, and this equation can very well be written in this form, in a functional form, half at squared as well, and it's just as good. We've shown you the derivation of this, and you also know that at any time you have a acceleration, you do its integral, you get the velocity function. When you do the integral of this velocity function, you get the position function. This is something you should memorize because it can save you a lot of grief. Going backwards, you have a derivative procedure from the position, you get to the velocity function. Taking a derivative of the velocity, you go back to the acceleration function. But in this subject right here, we're looking here at this top loop in this direction, and you know it's not hard. For an object which has a gravitational pull on it in terms of acceleration of 9.8 meters per second square, you know you could technically put a minus here because objects will go down towards the ground from an altitude, down towards the ground, the vector pointing downwards. You can do the integral of this and you can get to the velocity. You can do the integral of that and get to the position. The only condition over here when we talk about this interesting phenomenon is that the object must be falling down a finite distance. It cannot be in a region of infinite space where it will fall down forever, in which case this interesting phenomenon will not be seen and we will not notice it. So for all objects having a finite free fall, this phenomenon, this interesting phenomenon will apply, and let's talk about it. So let's talk about this interesting phenomenon for an object in free fall, and we're going to talk about it in terms of two cases. In case A, we have an object that is merely dropped from a certain altitude and it's placed into a free fall motion. You hold it, you drop it, and it falls freely. In the case B, an object is positioned at a certain altitude but it's thrown with an initial velocity, and then it enters free fall and it hits the ground. So these two cases, in one case you have an initial velocity of 0, and the other case you have an initial velocity of 10 meters per second. The phenomenon is this, that you would assume that an object which has been thrown with an initial velocity and it enters free fall, it should hit the ground with a significantly higher velocity than that object that is merely dropped, and you would expect this velocity at impact for case A to be significantly less than the velocity of impact for case B. But the phenomenon is this, that there will be a little difference between the both cases. That is, both the velocities at the time of impact for case A and case B will be significantly similar, contrary to what you would think. So let's actually show that to be the case. If you have an acceleration over here of 9.8 meters per second square, you have to do integral of this. You do the integral of 9.8 meters per second because this represents our acceleration function, and you do it with respect to dt, you get 9.8 t. This is meters per second. That's my case A. Over here what we have again is the same thing, 9.8 meters per second square dt, and you do the integral of this, you get 9.8 t, because this is simple polynomial integration. But here you have an initial velocity which taps on over here, and you have 9.8 t plus 10 meters per second. So now you can see the difference which comes. Here's a velocity function right here, and here's a velocity function over here. Now you take this velocity function and you integrate this, because you know the integral of the velocity function gives rise to the position function, and here you get 9.8 t squared over 2 meters, or you can say 4.9 t squared, which is the same. In this instance you do the integration of that 9.8 t plus 10 with regards to dt, and you'll get 9.8 t squared over 2 plus 10 t meters. So we've gotten the position function and we've gotten the velocity function for both of these. This is our position function. Here is our position function for case B. So you can see how everything is coming into play. Now let's get into our scenario over here. In case A, an object is dropped from a height and altitude of 1,000 meters. What is the time needed to hit the ground? It's not too hard. Look at this 9.8 t squared over 2, the position function. you look at 9.8 t squared over 2 and you equal it to 1000 is equal to 1000 is equal to 9.8 t squared. You solve for t and you can easily come up with a good value over here, and you get 14.28 seconds, and the phenomenon will become apparent soon. In this instance, it's still again dropped, but it's thrown from again an altitude of 1000. Here you have 1000 is equal to all of that. 9.8 t squared over 2, I'm just going to write that as 4.9 t squared plus 10t. But now you cannot simply just solve for t, you have a quadratic equation, you have to bring in the quadratic formula. 4.9 t squared plus 10t minus 1000 is equal to 0. Use a quadratic formula. When you use a quadratic formula, you plug in your a, b and c. You have a minus 10 plus and minus b squared, which is 100, minus 4 times 4.9, which is your a times c, all over 2 times a, 4.9. When you do this, you're going to get two values, a positive and a minus. You'll only stick with the positive because time cannot be negative. Now in this instance, I'm getting a time over here, and I'm taking the right answer over here, the proper answer, the positive answer, because you know you have a quadratic equation and you would have generally two x-intercepts. One of those x-intercepts would be in the negative and the other one would be in the positive. I'm sticking to the positive, and that's what we have. In this instance, case A, an object that is merely dropped, it took 14.28 seconds to hit the ground, which is reasonable. For an object that was thrown and then it entered free fall, it took 13.3 seconds, so a little quicker, which is good because it already has that initial speed, so it's going to hit the ground sooner. Now the interesting case will arise when we actually look at the velocity at the time of impact. The velocity at the time of impact, you're going to use this equation right here, the velocity function. Velocity at the time of impact is really 14.28 seconds, and you have 9.8 times 14.28. I'm looking here at this equation. I plug this in and I get my velocity at the time of impact, 9.8 times 14.28, and I'm getting 139.9 meters per second. That's my velocity at the time of impact for case A, for an object that was merely dropped and it entered free fall. Let's just come over here for case B. We're going to come right over here because of space limitation. We'll come over here. For the case B, for the object that entered free fall after it was thrown with an initial velocity, we're looking at 13.3 over here. We're going to plug everything here into this equation right here. 9.8 times 13.3 plus 10, and we'll get this value over here. Let's plug it. And we end up having here a 140.34 meters per second for case B. And look at the stark difference between the two. 140.34 and 139.9. You could literally round them up and bring them to the same value of 140. And now you see the interesting phenomenon. For an object that is merely dropped into free fall, and for an object that is thrown into free fall, the velocities at the time of impact will generally be the same. That is, that initial velocity has little to no impact for the velocity at the time of impact, simply because we're talking about here for a finite free fall. If it was an infinite free fall, then you would have time to actually go to a higher value over here versus this. The reason why this is the case, or this interesting phenomenon comes into play, is for two reasons. Number one, we're talking here about a finite free fall, that there's this fixed altitude. We're looking at that. And the second reason is this: because this case had a higher time, it took longer to hit the ground. This case B took less time to hit the ground. When you plug everything here into the velocity function, you have a compensation effect. Longer time over here, therefore slightly higher velocity at the time of impact. Slightly smaller time over here needed to hit the ground, therefore slightly lower in terms of compensation for the velocity of impact, because this object here in case B took less time to hit the ground. It was in a free fall motion for a shorter period of time, therefore it did not have the time needed to really pick up on this speed and exceed this by an excessive amount, and therefore that interesting phenomenon with regards to free fall comes about. Case A and case B, and you've seen it before you. Case A, object dropped into free fall. Case B, an object thrown into free fall with an initial velocity. And that's all I wanted to show you for this video. I hope you enjoyed it. Thank you for watching. Have a nice day.